with you all being back. We do have at least one more break, but a lot of speakers this afternoon, some fantastic information, and I'm going to kick us off right away. But before that, I missed a critical duty. I forgot to tell you to fill out your surveys again and hand them into the little bowl, and I must have been told about 10 times in the break, Richard, you didn't remind them to fill out their surveys. Apparently, my salary will be reduced if you do not hand in your surveys. You do not wish to see a grown man cry and sob. I'd be on negative money if that was the case then. So fill out your surveys, help a poor boy put his kids through college here in California, and that would be, I'm only joking by the way. I don't actually lose money if you don't hand in your surveys, just in case you're actually worried for me. I'm not that bad. So please hand in the surveys, and now I'd like to hand over, where's Robert down there? I'd like to hand over to Robert Ryan. He's going to tell you all about new technologies for deploying big data applications. Robert is one of the principals here at Fujitsu North America. He will introduce himself and his distinguished panelists. Robert.
Thank you very much, Richard. Thank you. My name is Robert Ryan, as Richard indicated. I'm joined today by Makiko and Anab from our research labs in Japan and America, respectively. Our topic this evening is going to be on big data and some of the research projects and innovation that we have going on within that particular space. So you've probably heard this already from other presenters, but Fujitsu is driven by a vision of using technology to better society. There's a strong belief that the technologies that we employ should somehow enhance society and bring forth a more prosperous existence for human beings. In order to do that, we will be leveraging, or would need to leverage, big data. We'll need to be able to leverage some of the information that is being produced by sensors, computers, and by social media to be able to drive insights and enable mechanisms that will then allow us to act or change the behavior of to engage people and change the behaviors of how companies may interact with us. So some may be wondering what exactly constitutes big data. So big data, from our perspective, really is about the variety, the velocity at which data is being created, and the volume that's being created. Today we have sources like Twitter, we have sources like Facebook and other social media platforms that are building unstructured data. And then we have a host of sensors. Earlier today we heard about from the team on mobile about some of the sensors that are being used to monitor us. And the amount of data that's being produced by those sensors. Well, there are sensors that are monitoring our cars, our utility consumption, etc. All of these sources come together to create big data. The whole pursuit, however, of big data really is about gaining knowledge. It's about getting information that has some value to the actions that we may take. So in other words, it's not just data for data's sake. It's not arriving simply at an answer, but arriving at an answer that somehow enhances or addresses the context that we are using the information in. Should we produce a particular product? Should I go into town today? Will there be traffic, or will the roads be clear? These types of answers can be gained by analyzing big data. As part of a big data initiative and innovation here at Fujitsu, Fujitsu has put together a big data initiative. The initiative is really around using big data to drive 5 themes. Those themes are around business process transformation, smarter marketing, better supply chain management, and productivity. Some of the concerns that we hope to address within the big data initiative is around making sure that there's responsible use of big data, and that comes down to data privacy. Additionally, we want to be able to provide fast use. So in other words, if I stood here for 20 seconds, to me it would feel like a minute or 2 minutes. So when you're looking to get an answer back about a particular item or context in which you're using information, for instance, should I buy a particular product? What do other people think about that product? And I'm leveraging big data to get that answer. If you have to wait a long period of time, it doesn't seem very useful to you. We're expecting information to come back in rapid form. And so to enable that, we're working on technologies around searching. And to talk more about data privacy and search, we're going to ask Arnav to come up, and he'll be talking about data privacy. And then you'll hear from Mikiko on searching unstructured data.
Hello everyone, and thanks for attending this talk. So I'm going to talk about top 10 challenges in cryptography for big data. So the big data revolution has caught us off guard, so as to say, because as the data is growing exponentially, so are the concerns about privacy. In fact, some reports indicate that privacy and security are some of the topmost issues that clients or vendors see in porting their data in-house to service providers. So in view of that, it's very important to invest in cryptographic technologies to ensure that all this vast amount of data has the right level of privacy, and at the same hand, also ensure utility of the data, because that's what big data technologies are about. So the first question in many people's mind is, what is so different about cryptography for big data? Why is it different from traditional cryptography? So I would like to divide this answer into two parts. So there's the part of big, so which talks about, you have to scale up the existing solutions for volume, variety, and velocity. That's there. You have to retarget the cryptographic infrastructure to the big data infrastructural shift. So you have to talk about how to use cryptography in NoSQL data stores and how to use it in Hadoop clusters and so on. But there's also some emergent phenomena due to the abundance of big data out there. So there are private databases and public databases, and it's amazing how much correlation people can derive and unearth sensitive data if it's not handled mathematically correctly. So here the topmost problem, I would say, is balancing privacy and utility. The second point is, how do you enable analytics and governance on encrypted data? So encrypted data by itself is not geared to provide governance on semantics of the data. But new cryptographic technologies would enable you to do that, and it's important to study those technologies. Lastly, how do you reconcile authentication and anonymity? This is a very important problem because you want to ensure that the data that you're seeing has integrity. It is coming from the right sources. It's not coming from spurious entities or attackers. But at the same time, you want to maintain some degree of anonymity for the people who are producing this data. So how do you reconcile between these concerns? All these balancing acts are the new face of cryptographic technology. So with this in mind, so we are leading this working group called Cloud Security Alliance Big Data Working Group. It's part of Cloud Security Alliance, which is an industry consortium. And as one of the works in that working group, we have come up with these 10 challenges in cryptography for big data. And in particular, we have divided them into 4 buckets. First, we have the infrastructure, in which we are talking about communication protocols, key management, and so on. Then we have encryption technologies. How do you do access policy-based encryption? How do you search and filter encrypted data? How do you outsource computation securely? The privacy aspect has many facets. So you have to talk about secure dissemination of data. How do you collect securely? And how do you collaborate securely? And finally, how do you govern the data that you have in store. So you have to ensure data integrity and proof of data storage. So these are the top 10 challenges. In summary, I'm going to talk a little bit about 3 of them because I won't have time to go into all of these. So first, this is an example where mere anonymization is not sufficient to provide data privacy because of availability of public databases out here. So this is a very simple toy example which gives you an intuition of why that is true. So for example, this is a very popular example. So suppose there is a public movie database like IMDb. And you discover that user Joe Smith, who is not anonymous, likes movies U, V, and W. Right? And suppose there is a private movie database as well, like Netflix. So Netflix published their movie databases, supposedly anonymized. And suppose there we discovered that anonymous likes movies M, N, U, V, W, X, Y. Now it may turn out, and has actually been shown to be the case, that some of the combination of these movies is special, like they do not recur across many, many users. So it's highly likely by identifying these unique combinations, you can actually correlate the private database with the public database, and thereby unearth the private movie preferences of some person who wished to remain anonymous on some of those coordinates. So this tells you that merely anonymizing the data that you disseminate to the web does not give you absolute privacy. And this is a type of exploit that has been used in the literature many, many times. So that's about data privacy. I wanted to talk about some interesting, very exciting new technologies coming out in the space of encryptions. So traditional encryption just scrambles your data. So encryption is supposed to provide something called semantic security, which means that by looking at an encryption of a plain text, you have no idea what the plain text is. But with new technologies, what you can do is still have some capability to search and filter through them. So to give you a concrete example, suppose you want to keep your encrypted data, email data in Google, but you also want to have the cool features that Gmail offers, like searching and organizing them into folders and so on. So what could happen is that with these new technologies, what you can do is give a filtering token to a client, to a filter, that may be Google, and only you have the secret key. So what Google can do is, for example, just filter according to using that filtering token that you have given it, and thus you get to see the organization that you would like to see. But at the same time, nobody gets to know what's inside the ciphertext, only to the extent that they fulfill the filtering criterion or not. Finally, this is a very exciting new technology called fully homomorphic encryption. So here the idea is end-to-end encryption. So here the scenario is that you want to send encrypted data to the cloud, but it's not very useful if it's just encrypted, and you just use the cloud for storage only. So what you would ideally like is the cloud to perform computations, meaningful computations on the encrypted data. But at the same time, it should not be visible to the cloud, in the sense that the cloud should not be able to decrypt it, run its transformation, then re-encrypt it, because that makes the data vulnerable. And also, you're giving up possession of the key to the cloud. So how do you not give up possession of the key to the cloud, but at the same time enable the cloud to perform meaningful computations on it? So this is a very new technology. One of the first solution actually came up in 2009, and it has seen a host of papers coming up in the academic community. It's still 1 billion times slower than traditional operations, but things are looking up, and there are partial solutions, which we also have a demo of. It's from our colleagues in Japan, and I'll talk about it briefly. So when people ask me, it sounds like magic, how does this work? So briefly, so what happens here is that you're operating on the input data. So what you're doing to hide that input data is sending it to a very high dimensional space. And you represent programs as a series of additions and multiplications in that high dimensional space. So as you operate in the high dimensional space, the corresponding plain text also goes through the same set of transformations. But the cool thing is, it's never decryptable to the cloud. You can only decrypt it at the client. So to give you some idea of why this is hidden, it uses something called lattices. And so mathematicians have proved that in sufficiently high dimensions, it is somewhat hard to derive the closest lattice point. So if you introduce a little noise in the projected space, that makes it hard to decipher. So all this technology is how to make this happen. So in particular, we have in booth 24 a demonstration of this technology. It's not fully homomorphic encryption, but it's partial homomorphism, which is practical. And our colleague from Japan will be able to show you a demo of it working on a laptop, which is very, very fast. And this does genomic search. So please swing by the booth and ask us questions. So finally, I want to leave you with a note that cryptography is actually an enabler. You should consider investing in cryptographic technologies. And the reasons are that there is a realization across the industry, of course, that cryptography is imperative for cloud and big data. And mathematical assurance of trust gives people incentive to send their data to the cloud. But not only that, it's a significant research opportunity. There are significant opportunities to explore here. We saw that mere anonymization is not privacy, but that does not mean that you cannot have privacy. So you need to have systematic and mathematical considerations to take into account to actually prove that privacy is preserved. And then we saw that sophisticated techniques are in research stage or have limited deployments, which enable rich transformations and management of encrypted data. So with that, I would like to thank you, and please ask questions. Can I take questions now? Or?
We'll take questions at the end, so we'll let...
please hold your question till the end.
Yeah.
Now I talk about unstructured big data search. I am Makiko Konoshima from Fujitsu Laboratories Limited. We introduce our vision for evolution of big data. We think big data is very huge and mapped in object and phenomenon in the world. The problem of such big data are the number of attributes and elements is very large, so the conventional method is not available. Then analyzer is reducing attributes and elements for using conventional method, reducing manually. But valued data may be lost, this area data. In our approach, we use modern mathematical techniques to solve problems simply. Our research target is here. Our research target is just for us. We introduce one of our technology, unstructured big data search. We developed a high-speed similarity search technology. And unstructured data has two meanings. One is unstructured text data, for example, Twitter or Facebook. The other one is unstructured multimedia data, audio, video, and sensor data, like this. We use here unstructured multimedia data. Similarity search for unstructured data is expensive and slow because it's very complexity, high complexity. There are two main techniques. we convert raw data into high-dimensional vector using existed method. And our technique is to compress the vector data into simple bit string. The size of the original arrays, for example, 8,000 bytes. The size of bit string is, for example, 100 bytes. So the processing is very high speed. Second technique is our original machine learning. The search accuracy of a method is 2 times or more than. So we propose 2 kinds of service. This one and this one. One is a kind of service that speeds up existing searches performed on unstructured data. The other is a kind of service that performs approximate similarity searches. For example, let us consider a service in the call center, this one. If you store the record of conversation in an ear and want to search a certain word, for example, Tokyo, without our technologies, the processing time for such one word costs about 30 days. With our technology, the processing time is reduced to about 1 day. Another example is this one. This is a recommendation in e-commerce site. Please consider an electronic bookstore, and in particular, an electronic comic store. When one buys a comic, the e-commerce site recommends another comic that is similar to the comics. Our technology performs 100 times faster than existing method. Now I run a demo. This is this demo, the speech recognition demo. This is a demo image. There is a call center, a spoken word each other and approach the data center to the data, stored 2 or 3 years over. And in our technologies, the similarity search for all data with bit string, but this is very fast, and select a candidate and search with existing method. This is very slow, but the size is very small. So we can search fast. This is a demo image. In this Note PC, there are 96 minutes of data. The local city council's speech data, and in this demonstration, I'm sorry, this is Japanese, but you can apply every language. So the speech language about speech word about Tanto Daijin means a ministry of something, and the search is starting. So this processing only this Note PC. And in existing method, there is a oh no. Demo is failed. Oh no. So can I demo after?
Yeah, sure. So what we'll do is we'll give her an opportunity to reset the demo, and then we'll come back to it. It does work. I saw it yesterday, and it was actually amazing the speed at which it was able to search. So I'll at least vouch for its credibility. So what we'll do at this point is if we go ahead and take some questions, we'll save a little bit of time at the end to go back to the demo. right? And at least show you the technology in action. So if I would just go ahead and start, I'm going to ask Anna while Makiko takes a look at her machine. So in your discussion about cryptography and privacy, you talked about the need to maybe outsource the processing of large data sets to other parties other than the primary corporation. What are some concerns that one would have in doing such an outsourcing?
Right, so the reason for that might be you might have a very thin client. Like you might be a sensor node or maybe a mobile phone, which cannot handle massive amounts of data crunching. Also, you may not have access to the huge database that the cloud can have the capability of having. So that data may not belong to you, for example. So in those situations, you do not want to reveal your personally sensitive information to the cloud, but you want the answer back. So what you can do is encrypt your personal information with your own key, send it to the cloud, and do this homomorphic encryption, which generates the results of computing over that data, and then send back to you. So it has the ability, so the thin client gets the ability to outsource its computation to a more powerful computational and storage entity.
Okay, so if I got it, it's concerns around making sure that you're able to keep your data private. The technology that you all are working on helps you obscure the information that you would not want to share with a third party.
Right.
Okay, awesome. So how, with big data, because it's so going to be so pervasive, I think, and you're collecting so much of it, it has the potential to be really helpful to society. But then on the other side of it, there's concerns that we heard even in the previous discussion about predatory use of big data, in a sense. Do you think that this technology or other technologies that you're working on will address that issue and be able to help enable maybe some compliance within the big data domain?
Right, so there are two aspects that I see right now. So with homomorphic encryption, you can of course do these exact computations and give encrypted data to the cloud and so on. But utility is also to be derived of public data that is out there, because people want to research on, for example, retail data or financial data or health data. So there are many research industries that grow around having those data sets given to them. So for that, there is a second aspect of cryptographic technologies, how to disseminate this data in a privacy-preserving way so that you can still get meaningful answers, so utility out of the data, but you do not get the sensitive aspects out. So that's a question that's very, very sophisticated mathematicians are working on.
Okay, yeah. So what I'll do now is just take maybe some questions from the audience, and I think we will wait for the mic to reach over here in the corner. Okay.
Yeah, the question is about this new encryption method, FHE, if I don't remember wrong. The question here is, has the algorithm being put together to be more parallelizable, utilizing multi-core? Of course, I mean, there's also another issue, is has that been memory friendly, meaning that it will not bottleneck at the cache? So could you elaborate a little bit about the characteristics of this algorithm for the horsepower needed for the engine?
Right, so I think that it's going to benefit hugely from parallelized computation. The reason being that the current technologies that develop fully homomorphic encryption uses mathematical structures called lattices, which are vector spaces of high dimension. So vector operations can be done highly parallelly. There are some aspects of it that cannot be done parallelly, but I think most of the operations can be done parallelly. And yeah, people are researching that as well. Yes, I think compilers help in identifying or taking the hint that some operations are vector operations. That would be helpful. Please.
If we wait for the mic just so we can hear the question. Thanks.
Two questions, please. One, you mentioned homologous encryption. Is that, can you do strong encryption with homologous encryption or only weak encryption? Second question.
Sorry, I didn't get the,
can you do
encryption?
Strong homologous encryption or is it only weak? Second question. You mentioned that some searches could be expressed by addition and multiplication. To what extent can all searches be expressed as that, or is it only a small, limited class of searches?
Okay, to answer, if I understood your first question correctly, you're asking whether homomorphic encryption is a strong encryption or a weak encryption. So I'll take that in a technical sense. So when we, in the cryptographer's world, when we describe an encryption scheme as very secure, we think of a property called chosen ciphertext security. So in chosen ciphertext security, what happens is that even if you have the power to decrypt some messages, you still do not get the power to decrypt a message of a challenger. So if you are not directly decrypting a ciphertext that was given to you as a challenge, you don't get the power to do anything else. So that's the strongest form of encryption that we encounter for traditional encryption. Now, for inherent purposes, that notion of security is not satisfied by homomorphic encryption. It cannot be mathematically a CCA or chosen ciphertext secure security, but it does satisfy the next weakest notion, which is called CPA, or chosen plain text security. So if you do not have the power of decryption always, then you can still prove that the homomorphic encryption is notion satisfies that notion of encryption. I don't know if I answered your question correctly, but yeah, that's what I have in mind. The second question, so you talked about searches. I'll talk about general computations. So it's a theory in computer science that any program can be represented as a circuit. And a circuit is something which has AND gates and OR gates. So if you take that representation into the ring space where homomorphic encryption operates, high dimensional vector space, even there, these operations, additions and multiplications, are Turing complete, which means that any operation can be represented in that way. But maybe it increases the size of the program quite a lot.
So I'm going to pause on questions for a moment and just loop back over to our demo that does work, so that you can get some advantage of understanding how fast the technology is and its benefits.
I'm sorry for so this is a demo for speech search. For the query is the word Tanto Daijin. This is just Japanese, and the database is 96 minutes of Kawasaki City Council. That's the local government, and now we start. Oh, okay. Now we start the search. In existing method, the search use the search time is 3 minutes. But our technology uses only 10 seconds under. So this is only 6.9 seconds. So this is very fast, and three times detected to speak Tanto Daijin. Let's hear to. Oh, I'm sorry. What?
So basically what would normally happen, we don't have the audio on, is that the search was completed looking for the search term. And then there was 3 indexed items that were found. So it found the instance of the word 3 times, and the markers that you see at the bottom there, the 3 points, are the actual index location in which it was found. So there you go. We have the technology. So here we go.
So now I play the word to detect. So I can detect it.
So So if you have any questions on this particular technology or on we'll continue the discussion. So we see a question here in the back left.
Well, I understand that this search algorithm works much faster. So what's the probability of hitting the false positive and the false negative?
False positive.
Meaning that the algorithm thought that you found something matches the key, or you found something which in reality really matches with the key, but the algorithm recognizes that it's not matching.
So the accuracy of the...
Yes, our search is only the wave of This is our technologies in little bit detail. And the feature value is extracted by raw data, and this side is the existing method. And our technology is to convert to bit string from the feature. So not is this is a key, but
so in regards to the accuracy then, right? What she's explaining is that the data is converted to a bit stream. The bit stream then is compared, right? And it's mapped. And so what happens is that the things that are likely to meet your search coagulate, for lack of a better term, into a particular area. That is your first pass, right? It's part of a solution, not necessarily the answer. So it's saying this group, right, of this set is more likely to be what you're looking for. Then after that, there's actually a more comparative search that's done on the smaller set, which is why you get the boost in speed. You can narrow down to the likely candidates out of a large set very quickly, and then do a more detailed analysis of that smaller set in order to arrive at the items that actually meet the criteria of your search.
For the first pass, for the first pass mapping,
yes. Loss?
For the first pass of a mapping to the bit stream, will that be a lossy process, meaning that some data might be dropped, or it's a lossless? I mean, it's a high fidelity translation.
In this process, yes, loss. So this is a nearly approximate search.
Oh, so it's a lossy. It's a lossy compression. Oh, okay.
Yes.
That's fine.
Lossy compression.
Okay. Do we have any other questions? Oh, see some hands up in the back.
Arnab, can you talk about this filter token that you talked about? What is it? What type of key is it? And what type of access does it have?
Right, so a filter is something that you generate from the secret key. And so the property of this filter is that from the filter itself, you cannot generate the decryption key. And from the public key, you cannot generate the filter. So it's something sitting in between the public key and the secret key, without any way of going towards the secret key from the public key. So it's a higher privilege than having the public key in a sense. So if you give that token to somebody, that person has the power to understand whether a particular ciphertext achieves the criterion or not. But beyond that, it learns nothing else. Whereas if you don't have that token, you get no information at all about the plain text. So it's an intermediate secret key, so as to speak. But it still does not give you the power to decrypt.
So do we, any other questions in regards to either one of the technologies? I do have one question, and it's around the I/O related to the search. So does that, does the searching that's done, the bit conversion and the set analysis, does that have a high I/O cost, and is there any limit, head limit that you'll reach in doing such a search?
So I think that please. I think that this one is into the memory, because this size is very small.
Okay. So in essence, by converting to bits, we're able to use less I/O and to do the analysis and storage of some of the information, at least in memory.
Yes.
Okay. Yes. All right. Do we have any additional audience questions? So I see a hand up here in front.
Is it possible at this point to achieve privacy, given that so much information is already out there? And in addition, more and more databases with private data are being broken into, and the information released, at least, to some interested parties who are willing to pay for it.
Right, so technically what you're asking is called composability. So this is the notion that you have an algorithm to convert your data to a sanitized data set. Does this sanitized data, in conjunction with public information out there, give you anything more? So there are notions of privacy out there which exactly formulate this in formal language. For example, one of the notions is called differential privacy. So the notion of differential privacy is that given the background knowledge that you have and answers to the queries that you are receiving from the sanitized database, can you derive any more knowledge than that? So you cannot say, I cannot derive any knowledge because I have that background information. So I can derive whatever I want with that background information. So this notion of composability is that, are you deriving anything more? So, and the development of protocols that have followed this notion gives you an approximate level of privacy. So you still have a quantization, a metric about how much more your sanitized data will reveal about a particular individual given the background information that you have. So it's always bounded.
Yeah, and so from a practical standpoint, meaning just a person view, I think that big data is going to cause us to have discussions about who actually owns the information about the individual or entity. There are already countries that have laws around who owns that information, because although we may have privacy, we may be able to enable privacy via technology to some degree, I share my information with those I'd like to have that information. And often that information is not necessarily kept in a encrypted form. For instance, we all have iPhones, Androids, etc. We've downloaded Candy Crush, Angry Birds, and some of the others. And they all have the ability maybe for you to create a login or to register. Well, you're still giving a bit of information to that company, and without necessarily understanding how they might be storing or securing that information. And so that information now is theirs. If they decided to shift that database to a partner to go advertise to you, they potentially can. So I think the notions of privacy will change, but the laws, I think, have to be enabled to allow you to become as private as you'd like to be. In other words, to retract the license to use my information from an entity that I provided my information to, right? Except the government, obviously. So any additional questions that we have on search or encryption?
You were saying that there's the public and the private key, and then there's something in between that you're able to use that allows you to search the encrypted data. And I like the fact that you can search it without having clear text floating around. But does that intermediary that you have in between allow brute forcing of decryption of that data to occur in an easier method? And are there any countermeasures in the design to stop someone from brute forcing if that intermediary does make it easier?
Right. So it's one of the hard questions, actually. So it's one of the questions why it has been difficult to construct. So what has been difficult is to come up with mathematical constructions that allow for this room to move about. But the way it's formulated is the mathematical assumptions that are laid out is that it's going to be hard for you to achieve anything other than the searching capability, given the intermediary token.
Understood, but if I can search, I can find patterns, and that could help me.
I see. Okay, so to answer your questions, you can do everything by having the capability of searching, and what it does not provide you to do is to do anything other than that. So you can, of course, do everything you could by just having the searching capability, because that's given to you. But the guarantee is that you won't be able to do anything more than that. Sure.
Okay. And any additional questions on the technology before we end the session? All right, well, I want to thank everyone for participating and listening to us talk about the advancements that are being made. I guess the takeaway here is that there are technologies that are being developed that help us leverage the amount of data that we're producing as a society with the objective of enabling that society to do things that it wasn't able to do before, predict maybe the fact that there's an accident ahead, as you've seen in some commercials, or enable me to determine whether I should buy here or there, or what products I should look at, or maybe even to affect how I might approach my health care from the previous discussion we had earlier today. And those technologies and innovations, Fujitsu is really, I guess, leading in creating its data center initiative and its big data initiative and products. And I think you can do some Googling and searching. You'll see that we released the first 10 this past week. And I think it'll be an interesting read for you to take a look at some of those technologies. And if you have any additional questions, Anab and Makiko will be roaming, so you feel free to approach them with any additional questions that you may have. That's it. Thank you very much.